I'm Shafeeq, and today I'll be talking about simulation tests for API-based systems. The title is slightly different from what you might have seen in the site outline in Lanyard, but the talk is pretty much the same. I work in Niranso. Niranso is a tech cooperative here at Bangalore. We do primarily clojure consulting, and I've been with Niranso for the past year and a half and been writing clojure that long. So this talk is primarily based on my team's experience trying to build a simulation test suite for a client project that we worked on. So the structure of this talk is like I would go over the problem statement of why and how we came to write this test suite. Then we will revisit some terms that most of you here would be already familiar with, and some prior art in the field of generative and simulation testing. And then we will go on to actually building the sequential steps in actually building the test suite. We will see the libraries and tools that we used, and also some steps involved in actually building the suite itself. Okay, as is the custom, let's start with the definition of simulation itself. What is simulation? It is the imitation of a situation or process, or more to our context, it is the production of a computer model of something, especially for the purposes of study. With that in mind, let me explain the project that we actually worked on. So the system is a API-based payment system. So all it exposes to the outside world is this set of APIs, and there is a Swagger schema for it. And different clients can use this API to build mobile applications or build smart other devices to integrate into this payment system. And the system itself is designed to be very distributed, primarily so because we want to, firewall away all the payment systems somewhere and put something near the client, or any reason that you can think of for writing distributed systems other than that I already described. So with that in mind, the system has a sort of a middle messaging layer between all the endpoints in the system. So all the requests go through this messaging layer, and the actual API, HTTP API also is like a pointing to the messaging system in somehow. And the project was very fast-paced. It's a early stage startup, I would say, but pretty big also. We were an all-clojure team building this system. At the point in time when this test suite was written, it was like 5 of us people writing clojure. Development was fast, and for the API that we exposed themselves, we had a manual QA team hitting the APIs with all kinds of inputs and all kinds of other things they could think of, but it was mostly slow. So we would be churning out new features, new use cases of our system, and we will have to give the entire specification of how to use this to the manual QA team, and they will have to, they later come up with it. They reported some pretty good bugs, but as is the case of all the manual systems, it's slow. So let me explain the system slightly more in detail. Imagine you are walking into a brick and mortar retail store in your neighborhood. What this system enables is that you can walk into the shop, you can put things in your basket and take it to the checkout counter, but the point of sale at the checkout counter is a smart POS, by which I mean it's just connected to the internet, and by internet to the system that we have in place. So as soon as the checkout operator scans any item, you can in real time see what's being scanned in your mobile application, and you can later, at the end of the process, pay using your mobile phone with your card. So it's sort of a hybrid between the usual retail stores and the e-commerce, and binding them together, or uplifting the traditional retailers to the e-commerce space somehow. So the flow that I just described, the shopper walking into a shop, buying some items, checking it out, and paying it. This is what we call a flow in our system. This is for one shopper, and it's a pretty simple process of checkout. What actually we might have is several shoppers queuing up in front of maybe a limited number of POIs. So our system has to, concurrently manage these shoppers who, while waiting in the queue, might be adding new cards to pay. All kinds of scenarios that you generally see in a payment system. So that's a more realistic approach for it. But the system itself has to deal with this checkout process for multiple retailers they have tied up with. So this is the process that we want to put under test. So in general manual QA, or even the functions or the tests that we write as developers, wouldn't really account for this entire usage of the system, maybe how it's used in production. It's not very easy to write it down or to test it with, and probably take some time too. So our goals to write the test suite was to simulate all the possible flows in a checkout process. There might be more than one checkout process where you wouldn't actually walk into a shop, you would just buy something from your mobile directly clicking on an ad. So there are many checkout processes, many ways you can go about it, and we want to simulate all of it. Not only that, we want to automate the creation, execution, and reporting of these tests, and thereby run the test in parallel, and hopefully we'll catch some concurrency bug, because that's something you don't always write tests for. And so we built the system to some degree, and I'll show you a demo of how it looks like. So this is the REPL. I run tests in our test suite, and this is the report that it generates. So what you see here are 10 instances of the checkout that I just described having been simulated and run in the system. So all of them has been, most of them have been complete. One of them completed only 17 actions out of 18 actions that it simulated. And it had an inactive basket exception. And most of them reached some sort of checkpoint. Some had canceled transactions. Some have completed payments. So this is the report that our simulation test suite finally generates. But let's maybe look at some more interesting thing. I run the test again. It will produce a similar output, but third time is the charm, so I run the test again. Okay, this time we have an error. So now in the reporting, we see that that particular flow, a sequence of actions, has failed. And right beneath the initial report, we have the entire flow itself, the sequence of actions that went into it, described here. And below that, the actual error that caused the test to fail. This says basket not editable in this case. It also has the request that went into making that request. So that's what our final test suite looks like. And we'll see how we got there. This is a Slack report that we generate. So we have this running in CI automated. So it runs periodically these tests and report it to CI, Slack. Okay, with that in mind, let's take a few steps back and revisit some things that we already know. I'll start with example-based testing. So example-based testing are the tests that we usually write, our usual unit tests. Functional tests, integration tests are all probably example-based tests. And usually you have an input that the developer itself thought of and put it down. And you run your code under test against this input. You take the output and validate it against the output that you expect. So you have input and output that the programmer know already, and you validate it against it. And this is typical example of an example-based test. It's the regular clojure addition. There are some inputs, some outputs, and if you are particularly savvy, you might test the edge cases with negative numbers. But the problem with example-based test is that it's very limited in coverage. It covers only as much scenarios as the developer can think of and put down in code. And if you have features, stories, functions coming in very rapidly, you don't always test all the parts of your system. You just look over some of it, just test the happy path and get over with it. So to alleviate this problem, you have generative testing. So in generative testing, the machine can generate inputs for you. You don't have to think of every input by yourself. And if the machine generates this, it is totally random. Could be based on the schema for your actions. But the other problem here is that you don't know what you validate it against beforehand, because it's generated and it's random. So what you could validate these tests against are properties. These are properties of your system. And properties of your system are invariants which doesn't change for any input that the generator might generate. Examples for properties of a system very easily are mathematical properties like idempotence, commutativity, associativity. So for addition, you can think of function, these properties, but most often your system also has these properties, although they seem very algebraic. Think of, if it's a payment system, you probably want your payment to be idempotent. And you don't want to, double charge your customer if the request happened twice. And some of them may be commutative and associative, some of them may not be. So all this you can test using generative testing and explaining the properties of your system in the test and validating it against. Another kind of property-based testing is simulation testing. So property-based testing could be just for one of your functions or one of your API endpoints. In simulation testing, you are validating properties of your entire model of the system. And what you are striving to generate here would probably be the behavior of usages of your system as a whole, which most usually is a, sequences of actions that a user might do in your system. If it's a web page, the user might go to one particular home page first, then he could maybe go to some product page or profile page. So all these behaviors of usage, random patterns of visiting your sites, those are all the inputs for your simulation testing. The ideas that I just described, generative testing, simulation testing, as you saw, aren't very new. They have been in existence for a while. And here I will go through some of the talks that are very nice. This is John Hughes, a TED talk called Testing the Hard Stuff and Staying Sane, made at Clojure West. It's an excellent talk. So what he co-invented QuickCheck, which is a generative testing library for Haskell. And QuickCheck got so popular that QuickCheck got rewritten into many languages. We have Scala check in Scala and test.check in Clojure. So what he describes in this slide is that the way QuickCheck works, it generates sequences of API calls, right? And tests those sequences against the system. And in some of the generated sequences, some actions will fail. Excuse me. But what's interesting about QuickCheck is that QuickCheck can actually, once it encounters a failure, reduce the next generated sequence to those minimal actions, sequence of actions that triggers the error you just saw. So if the error arose in a sequence of 20 actions and the error is just a very particular sequence of 2 actions, it can actually shrink the input, right? Shrink the input to the minimal failing example. And how you test the system is, of course, by making this API call and putting down the model of your system. So most often your system has state machine. Your entire system would probably be a state machine, right? So you put this down in writing in your test suite, And after you make each API call, you will have post condition to check that this API call made a valid state change in your system. So that's your validation problem. So that's quick check. Very nice talk. Please, if you haven't seen already, please go and see. This is test check. Test check is the Clojure port for quick check, and this is Gary Fredericks talking at Conch this year. He explains test check and generators used in it. Another nice talk. And so here in this slide, you can see what kinds of inputs you can generate using test check. It could be a Boolean value. It could be a vector of natural numbers. It could be a double. It could be one of these red, green, or blue elements. So all kinds of things you can generate. And for simulation testing, there already exists a tool called Simulant for Clojure. This is Michael Nygaard explaining Simulant. It was built by the Datomic team. Simulant is actually very well written. It is sort of a complete framework for simulation testing. We have taken so many ideas from Simulant. We have sort of extended Simulant maybe. But due to some nuances, we couldn't directly use Simulant. Okay. So these are the prior art. Now let's look at some other additional libraries and tools that went into creating the test suite. First of all, Clojure. And next is schema. I don't know if this is some, well, we used schema. We could argue that we could have used spec, but at that point, some constraints, by some constraints, we used prismatic schema. So all our actions in our system have schema, param schema and value schema defined for them. So the messaging layer that I just talked about earlier. So at that layer, there's always a validation whether the schema of the input and the output, matches the expectations. So we used schema to generate inputs for actions in our system. And test check has there is a plugin for generating schema values for test check. You can directly generate inputs given a schema. We also used a data script. A data script is an immutable in-memory database with a DataLog query engine. DataLog is similar to your Prolog queries, which was very useful because it's immutable. We could keep track of evolution of the state of the model and the system, and we could also write non-trivial queries to get the entire state or a specific part of the state of the system at one point in time. So that was good. This is a very typical data script, DataLog query. Here we are trying to find a specific flow and all the actions that went into it. So if you remember the error report that we saw earlier, we listed all the actions. This is the sort of query that goes into it. Now let me demonstrate some features of test check. So here in this REPL, I have required the test check generator and the schema generator to generate values from schema. I define a very regular schema called the person schema, which has a name, which is a string, and an age, which is an integer. So that's a schema. Now I can create a generator out of that schema using the schema generator function, which returns the generator. And now I can use test check to generate some values for the generator that I just created. Sorry. It's a video. So we generated some values. The first value, in both cases, were very simple strings, which is empty string and a very small number, which is a nature of test check that when it creates input values, it starts from the very basic, sort of smallest input and grows into a very larger output. But if you want a comparatively sized input, you can use the generate function. which would give you much more realistic input. So not only can you generate, there are test macros within test.check itself, which helps you directly write tests. So def.spec is very similar to def.test in your regular clojure tests, except that it can run several times the test that you just wrote using generated values. So here in this sum test, I am putting my sum function, which is just addition, under test, and I am going to generate 1000 input combinations for it. And here's what I can test, right? I can test whether the sum holds true for the identity property. Adding 0 should give me the same result. Is it commutative? Does adding A and B give me the same result as adding B and A? And is it associative? A plus B plus C, is it same as A plus B plus C? So let's see. I can define the test, go to the REPL and run tests, and it runs 1000 times. And there's also a seed value. So although the inputs are totally random, you can later recreate the same test by using the same seed. So this is a failing example for test.check. Although it's not a very particularly useful test, it can demonstrate that what happens when test.check test fails. So the test here is that you generate a vector of integers, and the number 42 shouldn't appear in it. Let's see a test that I've just written. Whoa, sorry. And when I run tests, it fails for so many values. So you see it failed, actually it failed for a very large vector of all those numbers that you just see, 12 minus 3 minus 2. But test.check on identifying the failure shrunk the input to the minimum example that can trigger the failure, which is just a single vector with a single integer 42. So this is really cool. Alright, let's move on to building the test suite itself. So these are the stages that went into the test suite. First of all, we generate the necessary input for the tests, put it into DB. Then we take the generated input, put it under execution, save the request, response, and the execution states all into DB. Then you later go into assertion phase where you fetch all this data again from the DB and run your assertions on it, property based. And then you can report on it. So all the data, everything goes into DB so that you can go ahead and inspect it later. And all this made possible because we used data script and DataLog. Practically save all the things. First step in generation is generation of the params itself for the action. Like I just mentioned, it's from schema, and you can use test.check generators. One particular feature here, though, is that test.check generators generate totally random values. So if you are generating a card number, you don't want 0 or 1 for your card number because it's going to fail, and it's not a very particularly useful test or a particularly useful input. So you can write schema constraints, which already exists for schema, to constrain these values, and the generators will honor them. After you have generated params, the next step is generate the flow. Flow is a sequence of actions, and flow also has some constraints. So most often you would find that if you are generating randomly some sequences of actions out of all the possible actions in your system, well, we have seen that the same action gets repeated many times, 5 or 6 times. So in a checkout process, if the shopper just goes into a shop and tries to associate his mobile phone with the POS repeatedly for 5-6 times, it could happen. I mean, maybe it could happen in some weird case in some real world scenario. Probably Dr. Strange goes into the checkout counter and bargains with the operator. But it's not very useful for a system, and there is a happy path we want to primarily focus on. So we devise some methods to constrain the flow also. There are also problems of idempotent operations. Idempotent operations are something you would be interested in, but how much and what kind? are they idempotent immediately adjacent to each other, or are they idempotent if it happens like 2 or 3 actions after you have executed one thing? So all this goes into consideration when you are generating the flow. To that effect, we first wrote some dependencies between the actions in the system. So here, for example, to authenticate a shopper, you should have created a session. And to provision a payment instrument to add a card, the shopper should have authenticated the session. To create a basket, you should have authenticated shopper, and that's the relationship how it goes. So for one action, you can define all the dependent actions on the other side. And some of them have 2, like to associate POS, you need to have created a basket in the mobile phone, and also you need to have an actual POS terminal in existence so that you can associate with it. So these are the dependencies. The other aspect of it is that after you have done an action, you can go off and branch to any other action in the system, right? Which is true also. The shopper could have associated his mobile phone, and then he decides, oh, I don't have a card, I should add one now. Totally possible. But what primarily focused on is one happy path of the system. So we define transition weights, which describes when you are generating these flows, what is the weight given to a particular action, given that you have just generated this one particular action. So if you have authenticated shopper generated now, 70% of the time generate add card, or which is provision card, the next time. And there is 30% which could be totally random, but dependent on the dependencies that we just described. This is sort of a transition matrix of all the possible actions, and which, more specifically translates into a Markov chain. With these 2, this is sort of how our DSL description for a checkout process looks like. There's a name, there's length constraints. You could have minimum of 10 actions and maximum of 18 actions in a sequence. You can change these. Some control on item buttons and transition weights and queue dependencies that we just saw. Given this, and trying to generate an action sequence, this is what you would get. So some actions got repeated, but generally they follow the dependency constraints that we just described, and also the transitions that we just described. So after you create session, you go to authenticate, then provision, create, associate, pause. So it's all falling in place. After you have generated this sequence of actions, you feed it off to another generator which would create the params for your actions. So here is an example. There is a POS terminal create. Q is nothing but an action, and there is params for it. The next one also has a params for it. But see how the merchant ID for POS terminal create is different from client create session. This is because your generator doesn't have state. It generates based on some constraints maybe, but still it's random inputs. So with that we come to the execution phase, where you actually feed these generated action specs, as we call them, into an executor. And here when you actually execute an action, you can use params that are dependent on your state. So say you have an action, you would query for particular parameters in your DB using DataLog queries, and you can replace those random merchant IDs with some ID of merchant that you have actually created earlier in the process. We have translated a particular flow where there rise an error that you actually are aware of in your system. This could actually translate into 400s in your API, right? Say in a sequence of actions you have created a session, then logged out, and then tried to create a basket. Totally possible, totally generatable, but doesn't make sense for a system. It's an exception. So we call them non-exceptions because we know about them and we can handle them. But that doesn't necessarily mean that they are wrong. That is the system working as expected. So that's what we call non-exceptions. And when non-exceptions occur or any other actual error exceptions occur, we stop the execution of the flow, entire flow there, save it to the DB and get on to the next flow. Otherwise, we just continue the execution, of course. And after we have executed an entire sequence, we move on to assertion. Like I said, we have to assert on properties, but one thing about properties is that they are really hard to, think of. So we started off with basic create, update, read, delete operations and trying to come up with some properties for them. Like if you create an entity and update an entity in a sequence, and later in some part of the sequence you have a lookup for the same entity, it should reflect the create and update. That's sort of a property. Or if you created 2 or 3 entities in the beginning of a sequence and later you have a list operation, the cardinality should match such that you have 3 entities returned in the list operation. These are, very quick properties that we came up with. And another, validation is of course that every action is okay. Otherwise the test should fail and report such. But these aren't all very particularly interesting. So what we eventually focused on was the state model of the system itself. This is the DataLog, sort of the validation function that validates that all the actions in your flow was okay. It's just a validation. But more importantly, here is a encoded state machine for our basket, right? So when you create a basket, given the state and the action and the response of the action, this is the new state of the basket you would expect. That's what one line in here signifies. So from new basket, and if you associate pause, your basket is in associate pause. So this is the state machine, state transitions for your basket, and if we have a flow where these basket actions occur, we can verify that the returned basket state for an action which actually made the call matches with the expected state that we have in here, which is a pretty good property. So if you are finding it, holding off on writing simulation tests because you're finding it hard to find properties, just remember that state machines make for very great properties. And after you have asserted, you move on to reporting and diagnostics. So you saw earlier this report. So if you are in this situation, you can dig into a particular flow. This is the entire timeline of that sequence of actions. And if I'm interested in one particular thing that failed, which is the post-update basket with the ID 501 something, I can check that and it will give me the entire response, including the exception that was raised. And it has all the request, response, and state, and also the generated params that went to it. So everything is saved in the DB, makes it super easy to later validate stuff. The system, although is not without caveats, primarily that although we have defined, the dependencies and transition weights, maybe we thought they would be okay. We have this working system. Maybe there is a better abstraction for them, right? So if you have some ideas, come talk to us. So this is the screen grab of GitHub issues that we created. We just randomly executed all the sequence, all the actions, right, without any flow constraints, just random input, random actions, and we came up with some 52 errors in like a couple of minutes. And we could just, create this nice machine precision tables with DataLog queries and closure print table, whatnot. In conclusion, simulation tests have been very good for us. Please use simulation tests. If you're finding it hard to come up with properties, just remember that state machines are there for you. And one particular interesting feature of the simulation test suite is that even if you are in a very fast pace of development, you are coming with new functions every day, all you have to do to cover your newly created function is to just add one or a couple of lines into your DSL. That's all. Thank you.